And we've got two amazing speakers for you tonight. First, Rich Seifert is here from Cooperative Extension Services. He's the Community Sustainability Coordinator, used to be just known as the Energy Guru, but now he's got an official Community Sustainability Coordinator title. He's going to talk through his solar design manual, which is for sale on the back table for $15 if you'd like to pick it up. There's only a few left, so if you want one, get it while you can. And then we have Thorsten Schlup from Rena, Alaska, and he's going to be talking about net zero house design. And he's done a few of those here in Fairbanks. And when I wanted to call the lecture, the net designing for net zero in Fairbanks, he said, we don't know, we don't have all the information yet, so we're moving towards it. So he'll talk a little bit about that, but a few of the things that are working well and lessons learned about implementing that here in Fairbanks. So just a reminder to turn off your cell phones, the ever-present cell phones. We just want to make sure that we give the speakers all the respect that they need. And just to give you guys a little bit of information about the Alaska Center for Energy and Power, we're an applied energy research group at the university. And we like to make sure that the information is in the hands of the decision makers to make good, smart decisions for Alaskan energy. And that can be everybody from state legislatures, community leaders, tribal leaders, to folks here in the room today that just want to know what they can do as individuals. And so we host this community lecture series every month. At ACEP, we focus more on community scale, but there's a lot of expertise throughout Fairbanks, and so we work with our partners to provide a good slate of talks for you once a month. Next month, on the third Tuesday, we're going to be doing one on ground source heat pumps, which is the premise of using the ground or water heat to heat your home in the winter. So it'll be an interesting topic. We've just completed a study, the Alaska Center for Energy and Power, with Cold Climate Housing Research Center, and so both of us will be presenting the results of that study. So it should be interesting. We're going to bring up the two speakers. They are going to switch laptops in the middle, but we do ask that you hold your questions till the end, and that way both speakers get a chance to talk. I will also let you know that there's a movie here at 8. And so we need to be out of here right at 7:30 so Adam can clear the room. And the movie is actually an energy movie called Gasland. It's about the hydraulic fracturing for gas down in Lower 48. So if anybody wants to stick around at $6 to stick around and attend, and we just want to say thanks to Adam at the Blue Loon for letting us be here. This is a fabulous place to watch a lecture. Again, we thank you all for being here. And with that, I'll bring up Rich Seifert. Rich, come on down.
Well, good evening, and most of my friends know I promised a great double feature tonight, and this is a really testimony to the interest, the incredible heightened interest of this topic. I wanted to set the stage for this because the subtitle to my solar design manual is Building Toward the Ultimate Zero Net Energy Alaska Home, and I wrote a piece in the Ester Republic, rah-rah for the Ester Republic. It's the true pulse of the community. I reflected on where we've come with this whole idea that we're going to talk about tonight of the ultimate design. I've often said in my courses that a fellow in Nome once asked me, Seifert, you've been coming out here 20 years now. Every time you come out, it's more insulation, more insulation. When's it ever going to stop? And I said, well, I think we've got the point now. We're at it. And so I titled that manual with this concept in mind, Building Toward the Ultimate Net Zero Energy. I'm reading from my article in the last month in the Ester Republic, and it really says what I want to set the stage with tonight. The best examples of the homes that have now been built by Thorsten Schlup and include his own home and the one he helped build for Carl Castle. These houses, it seems to me, represent a sort of culmination of the search for an intrepid, durable home which is always warm, cozy, quiet, affordable, yet able to cope remarkably well with the most extreme of climates. They're designed to extract the necessary heat and climate control with as much natural energy and with as little combustion as possible. That's a pretty magnificent thing to be able to say, but I sense its truth will be demonstrated over time. It's really an ultimate solution. The idea to need as little outside energy as possible to keep a humane and cozy tropical savanna climate inside a shelter in the subarctic. It's also the work of a meaningful and well-directed intelligence. That's nice to be able to say for a change, seeing what tragedies our species inflicts on the world at regular intervals. It's also our magnificent obsession come to good ends. Because I think Torsten, and you'll see this later on, has actually brought us back in Fairbanks to that edge of the obsession, the magnificent obsession to build the ultimate great house for the ultimate tough climate. With that, let me go right to the slides here. For those of you who've seen my solar design course, and this is in the solar design manual, this is where one of my best ideas and the entire seed for the net zero energy idea started. This picture is of the first ever, in my knowledge, zero net energy house attempt. It's at the Technical University of Denmark in, I'm still stooping here, let me not stoop, which is about 30 kilometers north of Copenhagen in Denmark, about 52 degrees north latitude. This house has several features that I want to point out because it has 5 elements that every zero net energy house has to have to succeed. And it started out in only being able to go zero net for heat, because at the time this house was built, in 1973, 74, it was opened, photovoltaics were not feasible, not in any economic way. They were about $500 a peak watt and only used in satellites at that time. So they only could do zero net for heat. But it's the first experiment where that was attempted and fairly closely succeeded. It has 5 different elements, and I'll point to them on the screen so you know. It has south-facing passive solar gain windows with movable shutters. That's actually 2 features. It has the huge 40-meter solar collector mounted vertical, which is what you want to do here, and a huge buried storage tank for energy. The idea being gain all the summer heat you can, store it in a big heat, insulated tank for the winter, see if you can carry yourself through. Now this is at a climate, by the way, that has about half the heating degree days that Fairbanks has. It's at 52 north, but in Europe that means it's actually like 42 north in the northern hemisphere in North America, because the Gulf Stream keeps that climate a whole lot warmer than at high latitudes than ours is. And the other thing it has, the 2 other things it has are a super insulated shell, which at that time was about R38, 12 inches of fiberglass. That was super insulated for 1973. And it has a first ever air-to-air heat exchange ventilation system, which is right here. And so those 5 things, the passive solar and active solar collection, the shutters, super insulated shell storage, and the air-to-air heat exchange ventilation system. There's actually 5, depending on how you count the solar. But anyway, that's where the idea started. Then we come 40 years into the future, close to 40 years, and this is a house that I feature. By the way, these fellows who did this house, Peter Amarong and Gordon Howell, two engineers, one's a contractor, one's an engineer from Edmonton, did this Riverdale zero net energy example for Alberta. It's in downtown Edmonton. It's a duplex. It has amazing characteristics, and of course, when you get to 2008, you can now go zero net with both solar, with vertical solar collectors here for heat and hot water, and also electricity with photovoltaics. And you can use the clever idea of using a duplex so you can share a common wall and save the heat loss in one wall, because you now have 2 family spaces sharing one wall, not losing heat against that wall because it's the same temperature on both sides, and you actually double the area for solar collection for the same heated spaces below. So if you build a whole block of these, you can see what an advantage that would be. And this is what we're looking at in how we moved. This is best looked at from right to left, which is sort of the Chinese way to look at this, I guess, but this is the way that the article was set up. But my house, off Farmers Loop, I bought in 2001, and it was a 1975 house. It was sort of like this, 2x4 house, R12 wall, ceiling. Well, we had a lot more insulation in the ceiling than that. but we were doing R12 walls by that time. A bit of insulation in the basement walls, but nothing in the floor, double glazing, pretty air leaky, so mine was a little better than that, but we didn't do very well. We were building houses, which is our problem now. We've got an entire housing stock built with cheap oil. And Alaska North Slope crude was $118.30 a barrel today. I check it every day. That's my magnificent obsession. And, you know, I don't know when we're going back, but I don't think we'll ever get back to $20 or $30 barrel oil. Maybe we will, but I've been wrong before, but I don't think so this time. By the 90s, we were building 2x6 too. We did that pretty quietly and without a lot of pressure. We went to our R28 to 34 in the ceiling. We had R20 walls. We started to insulate basement walls, nothing in the floor. We had better windows at that time. We were pushing the window option because we knew what bad things we had. We improved the air quality probably a lot more because we were starting to use air-to-air heat exchange ventilation systems. But look at what the Riverdale Net Zero Energy did. When I started my job in extension and I wrote the first solar design manual, actually exactly 30 years ago it was published, and I was only 12 years old at that time. Anyway, we're now using double 2x4 frame wood walls. Almost the entire building is insulated with cellulose, R100 in the ceiling. Important to point out, you know, these levels of insulation, this is about 18 inches of cellulose in the walls. This is about 18 inches of cellulose plus a little less cellulose and some styrofoam, and this is 6 inches of styrofoam under the basement floor. Incredible levels of insulation. Now, Alberta is the Texas of Canada. It has about half of the oil export comes from Calgary and the oil belts and unfortunately the tar sands, but it has also a lot of natural gas. So why do you take it to this limit? Well, the condition that was given for net zero energy is try and save as much energy as you can so that you don't ever have to buy it again, because the way you're going to get it is from solar. You have to build this house presuming that natural gas is never going to be available, so anything you spend for energy is going to have to come from solar. Solar is a whole lot more expensive, so it really, really pays you to save that energy, because once you saved it, you never have to buy it again. And that lesson needs to be really, really inculcated in our system and in our paradigm in the world, because time and time again you hear in politics, you hear it in public speakers, you hear it on talk radio, what we really need is cheap energy. No, what we really need is really, really efficient houses so that we don't need energy. That's what we really need. We need to escape from the need of combusting fossil fuels. And the best way to do it is this zero net energy idea. Well, people have tried this here. This is Kevin Maxwell's house. This is also in my design manual. I used this house because it was the closest thing I had to a very generic passive solar design, simple rectangle, straw bale house. He's got very operable, closable shutters facing south. These are windows that are patio door replacements. He's lived in this house for at least almost 10 years, I'm sure, maybe more. I don't know how long he lived in it before I first saw it. And I used this as a model kind of a house to analyze the passive solar design optima for the rail belt, starting in Kodiak, going up through Homer and Anchorage. And if I have time tonight, I'll get to that. I'm not sure I will. It's in my solar design manual. But Kevin designed all this stuff. I mean, it looks a little funky, but boy, is it functional. And having movable shutters, you want to make the world a better place for solar. Invent a retrofittable, affordable, movable, probably triggered automatically would be nice, but he doesn't have that option. He can actually move these from inside on a quarter-inch steel cable on a pulley. So he can close them and open them from inside, and I often go into the description of how he does that, but I won't tonight because we're pressed for time. And if you haven't seen it before, this is Carl Castle's house, and I was up there with my friend Phil Shadd before he finished it. This is the stack for the beautiful masonry wood masonry stove that's in the middle of the building. It's an octagon, and Carl explained to me that the octagon shape has several advantages, not just the fact that the center of the house is the masonry stove, so that every pie-shaped room can have a wall exposed to the masonry stove and therefore be heated by it. But also, an octagon for the enclosed space is actually a shorter perimeter and less materials, so it has that efficiency option. This is the passive solar design. It wasn't finished when I got there. He has a large water storage tank for storing the heat and many sources. This is going to be, I think, the windmill, and these were the solar collectors. And this is a house up on Murphy Dome. By the way, the walls are styrofoam, about R60, and this is just a very nice log siding. This is the front end, you know, the beautiful woodwork. This is Phil Shadd going in there. It's on the north side. I was obviously up there in the summer, or winter rather. And this is the beautiful masonry stove in the inside. And the back side of this is common to the back side of the shower, and a lot of other contact with other rooms. But this heats the major front portion area of the open space in the house. And this, and I think, I don't know, but Torsten can tell you who built his, but I think Dan Givens did this. I'm not sure, but I think so. Dan has been the go-to guy for masonry. He's a mason, and he's done a lot of them now. He had a booth at the home show. And this, you'll see more of this. This is Torsten's. I don't want to overplay this, but I finally got to visit it after the home show and all that. He has exterior shutters and solar design, very different, you can see, from Carl's house. And that speaks to this idea too. Both these guys are really doing research for the rest of us. And this is what I love about this community. It's always been that way. And now we're back at pushing the envelope again. Okay, well, I don't want to spend too much time on this. I do want to show this. Anybody know what this is? Some of you do. This is actually the new visitor center at the Denali National Park, and it has a facade wall. Oh, let me go back, sorry. That wall right here is actually a photovoltaic panel which is translucent. It's had 4 kilowatts of photovoltaics on it, and it provides electricity while it's shading the interior and preventing overheating. So it has this wonderful, many functional aspects to the facade, serving the building in a lot of different ways. This is the same building, allowing light to come in the top and light the back of the building, a clerestory. This is an architectural feature that I'd like to see more use of. All these things are in the solar design manual. We'll talk about it. Not going to talk about this a whole lot, but some other things about how to design from the sun. This is from Freiburg, Germany, which is the solar city, and I took a course there on integrating solar design into buildings. And this is a subdivision which you're seeing the north side of, 3 stories, very few windows on the north side, but a huge facade on the south. This is what it looks like. And we wouldn't do this, of course, here because we have this problem called snow. And so we wouldn't make a roof like this. We would maybe do a facade, but you might want to understand how to shade a south-facing facade from overheating. And what's shown here is very interesting because you can see the shadow line right there. This picture was taken in early September, and the overhang length is very strategically calculated to provide shading which changes with the seasons as the sun angle rises and lowers.
And we're right now close, you'd want a shade such that at the equinox, about half the window is covered. At the summer solstice, you'd want all the windows shaded so you don't overheat. And that's what this exact thing does. We can do this here. I have an example of how to do that in the manual. I always try and show this slide because this slide gets a concept and a magnitude of comparison across to people which is impossible any other way. If I told you that the world uses, 1.8 times 10 to the 18th, oops, there we go, wrong way, gigajoules of energy, you would never know what that means, and you would have no concept of knowing it. So what this particular slide does, and by the way, this is from the Danish Technical University, and it's actually from Norwegian renewable energy book that has been published in Norway, my all-time favorite country, next to the US, of course. It shows in comparative volumes of sequential cubes the amount of different reserves of fossil fuels and the annual solar energy, starting with the world's annual energy consumption in total, represented as a cube of that small size. As you go down, you can see the magnitude of comparison, and these are gas reserves of the entire Earth, oil reserves of the entire Earth in magnitude and comparison. Obviously, the gas reserves, if you took all the gas reserves and did an annual basis, that wouldn't last very long. You can see it's only probably a dozen or 15 years of reserves if you use all gas to do it, and that's the kind of comparison you can make here. Oil reserves are the next. They're shrinking, and they're in a finite amount. Uranium reserves are the next, and coal reserves are, of course, everyone kind of knows they're the biggest, and that's what we use in the United States more than anything, and that's what we use here locally pretty much. Not in majority, but certainly we use some coal. Now, the interesting thing is, these are fixed. This is all there is left in the known universe that we're ever going to get to anyway. And this is 1 year of sun. It's annually we get that amount. And the interesting thing about that, you have to take 70% right off the top of this because 70% of it falls in the oceans. It's not going to be easy to use that. But the magnitude of this amount every year is about, something of the order of magnitude of the entire coal reserves of the Earth, even with 70% of it taken away. And down here, you have two other little interesting increments. These are about 1% of all the energy that falls as solar radiation is converted by plants into photosynthetic carbon and captured as plant material, and another 1% is available as wind energy. Not all of this is capturable, and you certainly don't want to burn all the photosynthesis, but the whole world food system is in there every year. But that magnitude, that 1%, is about equal to the entire gas reserves in volume. So you can make that kind of comparison with this kind of thing, and I just think this is incredibly important. This is the slide I get the most requests for copies of from teachers because it can tell you things in really strategic, comparative ways that you cannot get with numbers. This is my own solar collector, and I just thought I'd put that up there. And here's what happens if you don't think through what happens with snow. I have a photovoltaic solar pump, and I put the collectors at 60 degrees. In spite of what I say in my solar manual, don't do as I do, do as I say. Put them vertical, if at all possible. You won't be sorry. That's what it looks like inside, and I'll go now quickly. I don't have that much time because I want to give Torsten a good shot, and I've got to change computers. But let me go to the solar design manual. Make sure I get the right one. Okay, I'm gonna, you can see this back at the, let me see, I'm gonna go to the navigation panels. And, well, let me just go. Okay, let's go, there you see, let me make it a lot bigger. There you can see Kevin's house again, super insulated, straw bale, solar optimal house of Kevin Maxwell. Here's the Canadians, here's the Riverdale duplex specifications. By the way, just for interest's sake, the Riverdale duplex costs $1.4 million. Each side is $700,000 list price Canadian, which when I went there was actually $29.95 US, but now the Canadian dollar is actually worth more than the US dollar, so I think we'll stay here. But I want to go to the optimizations that I do. What I did was try and use a computer program called F-Chart to see what kind of performance, what kind of savings you could get by trying to increase the solar gain, increase the insulation in various ways by modeling it with a computer program called F-Chart, which has a passive solar design optima, and I can set it up to say all these things. The window area, I can change the number of glazings, the slope of the window, the night window conductance, the day window conductance. I can make it appear to have a shutter. And I can do all these things, and I did it for Anchorage. And I want to show you some of the things that happen here. The first thing I did is model the solar performance of what is effectively an 80s house with an R value overall of about R12. And it used the equivalent, you can take my word for it, this is the backup heating requirements. This chart is complicated and I have to quickly go over it, but this is the amount of solar energy gotten on the windows. And just to make it clear that this is in millions of BTUs, and I have an easy way for you to understand what that is in terms of gallons of fuel oil. 1 gallon of fuel oil has a gross heating capacity of about 138 million BTUs. If you burn it at 70% efficiency, it's about 100,000 BTUs per gallon. So 10 gallons of fuel oil is 10 times 100,000 BTUs, or a million BTUs. So if you simply take these numbers and add a 0, you get the number of gallons of oil equivalent, just about. So the amount of solar energy on 100 square feet of window in Anchorage over the year is 270 gallons of fuel oil equivalent. Is everybody with me on that? Making a quick run here. And the load for the building, this is a 1,200 square foot house with 100 square foot of windows, no shutters. It actually takes 658 gallons of fuel oil equivalent. The backup heating of this 658 gallons of load, the backup system gives you 501, and the solar fraction is 23%. Of this amount, you can only use 23% of it to get your solar heating fraction, and this is the fraction of solar heating by month. You actually have 3 months of the year when solar heating gets you, but it's the months of the summer when you, of course, naturally would. That's what the sun does in the summer. Keeps you from having to heat. Well, what you end up with, and let me go to the final shuttered option, is in Anchorage. What I do is I go through several iterations and I come up with a 200 square foot window shuttered with an R values of about R37 all around it except for the windows. It has shutters on it of R10. And I have, remember what the amount of energy was in the first house, which is an 80s house, about 501 gallons of fuel oil. You end up with a house that uses 51 gallons of fuel oil. What that says is, it should be feasible. This is Anchorage, and Anchorage looks pretty good in this kind of an optimization. If you really super insulate the building, optimize it, shutter it, you can cut energy use by 90%. Now, there are lots of problems with this, because what happens in the summer and in the early spring is you overheat like crazy. And I have a solution for that. But anyway, you end up, and what I do is I say, okay, we don't really have shutters, so I'm going to say, what's the option without shutters? And it's not all that much worse. It's 72 gallons of fuel oil. But if you don't have shutters, it makes a difference, but you still do pretty well, and you get a 67% solar fraction. Now, these are pretty amazing numbers, and I could spend more time on them. In Fairbanks, if you do the same thing, you start out with a solar fraction. You can't do as well because it's colder and it's darker in the winter, and just, it's a harder place. We got to be more clever. But you start out with 757 gallons of fuel oil, and you can get down to an optimum of about, let's see, what do I finally get to here? 263. I think we can do better than that. Let me see. Yeah, 141. So you can cut about 80% in Fairbanks. Not great, but it's pretty good. You start out a lot higher, and you can get up to about a 55% solar fraction. You still overheat enormously, and by that I mean these numbers, 976 million BTUs, with the auxiliary is not necessary, but the load is only 2 and 0.1, so you're going to overheat enormously. You're getting much more sun on the windows than you need in the building, and so you've got to do something to shade it. I have a solution for that too. Let me go through this, and here's the solution, which is already out there in the real world on the President's house in Yankovich Road. This is the most, and I give credit, and this is all I'm going to do because I want to give Torsten 45 minutes or so, but this is the solution to overheating. It is a fixed overhang shutter, not a shutter, but a shade, which all you have to do is know the solar geometry. It turns out the highest elevation angle the sun reaches in Fairbanks is 49.5 degrees. So if you know your trig, you know that opposite over adjacent of 45, which is pretty much going to shade everything, is 1. The tangent is 1. So as long as the shade is as wide as the window is high, this shade will cover the window at the summer solstice, and will shade it halfway at the equinox when you start to overheat. It also, because of this design, it doesn't block daylighting, and it doesn't accumulate snow. So it does everything you need it to do, but it does block sun because it has a baffled shadow effect. So everything about this is done by C.B. Bettesworth. It is the single best creation I've ever seen an architect do in Alaska. And it's brilliant, it's non-movable, it's easy to build, it's easy to calculate, and it solves all those overheating problems with a fixed overhang, and doesn't cut down on daylighting all that much. So, lots of things more I could talk about, and it takes me 5 hours and a half with the photovoltaic chapter to go through the manual, so you're getting a really quick journey here. But let me stop there, and unfortunately we can't take questions because I got to dismantle my Mac addiction and let him do his PC. So I'll let him do that now. Hang on.
Fuel prices are where they need to be. We have a full house, so they will go up, and next time when we do this, there will be lots more people. That's at least what I believe. My name is Torsten Klupp. I'm a local builder in this town for about 12 years. I don't have a PhD, I don't have a PE, I'm just a builder, so bear with me. I'm not smarter than any engineer. Some newspapers kind of made that comment. I'm just trying to find solutions. I don't have any answers. I'm looking for them, and I have one advantage other people maybe don't have. I'm German, which doesn't mean a whole lot, but it means that I can read a lot of research papers which come out of Europe. And let me tell you this, Europe is light years ahead of us. I go over to building science conferences every spring, and it blows your mind how far behind we are. Why is that? Energy costs. I work quite a bit with the Cold Climate Housing Research Center. Anybody who is not familiar with our local research center, please go visit. They're doing incredible work, important work, and we're lucky to have them. Why are you guys here? I think that's one of the reasons. You know, we are basically on a concept of business as usual. We're building very inefficient buildings. We're adding lots of heat to them to stay warm in a cold climate, and somehow that equation doesn't work out anymore. So where are we going? You know, what's the direction we're heading right now? That's my question. And I don't have a crystal ball, but I don't believe it will be very pretty when we get to the top. And I wouldn't be surprised if we see $5 for heating fuel by next year. And then what are we going to do in this community? So we have a problem. We are in trouble. We know it. Evolution is catching up with us. And you know, the trouble really is not that we are in this position, but that we are still arguing about it. We're not doing anything about it. So we have come up over the last 4 or 5 years with some good solutions, green building, all of these great, you know, building standards, LEED, National Home Builders Association. Everybody comes up with some solution, but in the end, today, it's all greenwash. There's nothing to it. There's no substance. And then the autos industry, of course, they're catching up too. You know, we're really getting caught up, and that all doesn't help us. We are living in a very extreme climate, and it's difficult to build in Fairbanks, Alaska, more difficult than in most other places. And we so far have been gotten away with just building inefficient buildings because we could afford heating them. If you could heat anything with dense fossil fuels, because they have a lot of energy encapsulated, but if we are running out of these fuels, or if they're too expensive, we have a problem. And then, of course, here in our latitude, we have another problem. For 2 months, we have no sun, literally. And that is a problem if we're trying to heat a house with solar. So here I am standing saying, hey, it's not a problem. We just built houses more efficient, heat them with solar, and problem solved. No heating system, no utility costs. We're comfortable. But wait a minute, we are in Alaska, right? So is that possible? The average person says it's impossible, and I run into this a lot. A lot of people tell me even today, you know, it can't be done. This is silly. It doesn't make any sense. Because in the winter it's dark, it's cold. We have 40, 50 below. You cannot be without a heating system. So let's step back here. And Richard was putting up a nice slide about the first, you know, net zero home. But are we kidding us? I mean, people have lived here for thousands and thousands of years sustainably. Maybe in our standard, not comfortably, but they've lived here. And there's really nothing new about what we need to do to get to this point. And I certainly haven't invented any of this. You know, this person would know more about sustainable living than any of our new building science. And that's, I think, what we need to remember. Where are we coming from, and what are we trying to do? So going on, you know, this is basically my personal house, which I built because I believe we need to come up with solutions. And I personally am also tired of paying expensive utility bills. This is basically our second attempt of building a structure which will cope with this extreme environment and will be able to more or less heat itself. Carl Castle, his Octagon building was up on the slides. He's hiding somewhere in here, I'm sure. He was really the first person who walked up to me and kind of liked the ideas of, can we do this? And he was willing to jump out in the cold water and do this. And I think we have to give him a lot of credit for it, because without his house, this house wouldn't be here. Without this house, we wouldn't know what we know today to build this cheaper in the future for lots of people, because this is going to be the future if we want it or not. So let's talk about net zero. What is it? What's the energy balance basically we're trying to achieve? And I personally really don't like that term net zero because it's not an honest term and it's kind of a silly game. We're saying basically we have energy which we produce and energy which we consume, and the bottom line of it is net zero. On an off-grid house like Haus, how would we ever get to that if we don't have anything to really store energy? We're storing energy, thermal energy, in a big water tank. Okay, we can store electricity for a certain amount of time, but there are times when things are not equaling out. And on all of these net zero homes we see worldwide, that equation is always done on the grid. Lots of photovoltaic. It's sold back to the grid in the summer, and then in the wintertime, basically, that balances out the whole equation. If this is really net zero or not, I don't think that's really the crux. The crux is really we need to figure out efficiency in the buildings. And I personally really like Passiv House, which is a super insulated building standard from Germany. It was developed there about 20 years ago. There's about currently 25,000 certified buildings in Europe to this building standard. And that building standard basically gives us benchmarks. This is an efficiency level we need to be at where it makes sense. And that benchmark is what is really, really important. Net zero doesn't give us anything. It tells us at the end we need to be at zero, but it could be anything. It could be a huge, array of photovoltaic thermal collectors which offset the energy consumption of the building. And that's kind of what happens really, in my opinion at least, on a lot of new projects. We're getting back into this same old groove. Let's turn up the heat. It's more difficult, more expensive to do so with renewable energies, but it's possible. So instead of looking actually at the building, which is boring, we're going back to let's turn up the heat. So Passiv House, if you look here, there's two collectors. This whole building here, this is from the Solar Decathlon, that's a German entry. That whole building is basically a solar collector. So the baseline, what's the baseline for a building really has to be the building itself. We need to look at energy efficiency. And here, again, if you look back, how did people live here? What kind of a structure did they use? And how were they able to heat them? Can give us a tremendous amount of answers to this whole question. And I find it very interesting, and I keep looking back to the 50s, to the 60s, the last century. Now I'm looking back 1,000 years, and I find better answers with knowledge which we had back then than what we have now. So I think we're really arrogant about how we go about building. Passiv House basically gives us very few key principles. These principles do not change if it is somewhere in Frankfurt, Germany, or if it's in Fairbanks, Alaska. It doesn't matter where you are, these principles are the same. And it's based basically on airtightness. Why is airtightness so important?
You don't lose heat?
Anybody? Airtightness?
You don't lose heat?
Yeah, pretty simple. There's a lot less heat loss, a lot less problems. There's so many good things about airtightness. It still boggles my mind that the United States of America is the only modern country left in the world which doesn't really mandate airtightness in their building code. The 2009 Energy Code requires about a 7.0 air exchange at pressurized buildings of 50 Pascal, which is a total joke in my opinion. Passiv House basically says any building needs to be at 0.6 at a minimum for air tightness. And air tightness is really the cheapest method of increasing energy efficiency and also of ensuring that this building has a longevity and has no mold, no problems within the wall. Exfiltration is our problem. It's not moisture, it's exfiltration. So this is very, very important. And this continuous line is basically the air tightness layer. For heating demand, they're basically saying, hey, it doesn't matter where you live. We know what the magic number is built to it. what does that really mean for us? What's different about here than Frankfurt? We're a little colder. So what we need? More insulation. It's real simple. So, you know, here in the States we go basically, the way we design and build buildings here is we're saying, okay, let's put in R21 insulation. Let's not worry about air tightness because it doesn't matter. We find out at the end of the project how this all works. And then we oversize our heating system so we can make sure that we have enough heat to keep this thing warm. And then we build. And then at the very end, after everything is done, we energy audit the building to find out, hey, where are we actually at? And that's what we call a 5-star plus home. And a year later, the homeowner wonders, why am I spending $1,200 in heating every month? And it's going up. So here, German, they're illogical. They go the other way around. They say, okay, this is the magic number, so let's design to it. It doesn't matter where you are. Let's just design to it and then go from there. So they give us a heating demand number. They give us a total energy demand number. And we have to reach this to be able to reach passive house level. Very difficult to achieve here. Very difficult. So the Sunrise Home basically was my attempt to see if we can actually meet this standard even in our climate, which has not been done anywhere in the world. It's not just about Fairbanks. This hasn't been done anywhere in the world that far north. There's one certified building in the Antarctic, but they had a lot of government funding, so I don't count them. I built this thing on my bank loan and my earnings, and I still work for a living, and I still got to pay bills like everybody else. So this is not a research project. This is just somebody trying to do something. This is basically a spreadsheet which is used to calculate an energy model of building to passive house standards. We see basically up here the total magic number for space heating demand. If we have any engineers or any heating guys here, they will understand this number and what it actually means. It basically means you can heat a building like this with an equivalent of 2 air dryers and 2 toasters. That kind of puts it in perspective. How do we get there? The wall insulation is R75, the roof is R115, the slab insulation is R63, and that still would never get us where we need to be without really cheating here. This is basically the crux about our climate. It's all about windows. What Richard was showing us is so important. We need to get sunlight into the building. Once the sun is down, we need to make sure we don't lose energy. So what you see here, basically, what I tried very hard to do on Carl's house, which was impossible, was basically thermal shutters. This is our loss. This is our gain through windows on an annual basis. So this needs to be at least in balance, but now we have a plus, which kind of explains why I have not heated actively my house since February 16th. There's no heat input besides sunlight, which keeps me basically at 68 to 72 degrees since February 16th. That's not too bad. So here we're looking basically at the ground floor. In the back is the annual seasonal heat storage tank. In the front is what is heating the house for quite some time. That's the passive solar gain. And then just your average floor plan really. There's 2,300 square feet. 200 square feet are taken up by the tank. So it's an average, family home. It's nothing really out of the ordinary. Of course, it has an Arctic entry, which is very important in our climate. And my backup is the masonry heater. But the house does not have any fossil fuels. There is no boiler. There is no backup. It can only heat with solar or the masonry heater. And that is not just for heating, that's also for domestic hot water. Everything in this house is a prototype. I kind of came up with a different idea of a remote wall from Cold Climate. We used cellulose as our main base of insulation for several reasons. Cheaper, number one, of course. We want to build these things affordable. And then number two, embodied energy. It's a lot less energy than foam, and heat storage capacity within the building. The density of the material, it's medium weight versus lightweight, which is a huge difference. And we have data collection throughout the whole building through Cold Climate, and we've seen some really, really good data out of it. So here, what does it take to build a passive house in Alaska? Really, the short of it is it's a lot of insulation. You know, there's 12 tons of insulation in this building. So that seems really excessive, doesn't it? But doesn't it seem very excessive to have to pay thousands and thousands of dollars in heating fuel? I'd rather pay it once for insulation, and then for the next 80 years this building is covered. Another big feature of the house is basically internal thermal mass, which is insulated. I do that through a mass-loaded foundation system, which is super insulated. It's about 180 tons of sand, which are placed within 12 inches of EPS. That creates our thermal flywheel, basically, which allows me right now to store enough passive solar gain to, without 2 or 3 days of sunlight, I'm still comfortable. And I'm not overheating because I have places where this energy can go. Works really well. So there's a couple of shots of the foundation, super insulated. There's 4 thermal bridges, exposures of anything which can transfer heat out of the building throughout the whole building. There's basically water in, sewer main out, HV air in, HV air out, and that's it. There's no other penetration anywhere really. It's a pretty massive wall. It's 22 inches thick. So there's a lot of insulation, of course, which needs to go in. And the insulation needs to be on the outside. Our typical construction doesn't address that, but who in their right mind would try to stuff their down jacket in the wintertime under their parka instead of, putting it on the outside? It's kind of like ground insulation, why do you put a pad on top of you instead of under you? It all makes sense, it's real basic. Insulation needs to be on the outside in our climate. Interior shot also on the top. Basically, this building doesn't have a classical vapor barrier. One of the other points I'm trying to make with this building, that 6 mil plastic vapor barrier is a band-aid which creates more problems than it solves. This building is diffusion open. It can breathe to both directions. Diffusion is not the problem, it's airtightness. It's very airtight. The airtightness on this house is 0.48 at 50 Pascal. So it's completely airtight, but it allows moisture to travel. Here's a shot through the big window. In the back you see the in front of it will be the masonry heater, and the storage tank sits right in the back. A shot down the wall cavity. It's basically just a 12-inch big cavity filled with insulation, dense packed cellulose. That's the attic. That's kind of how our 115 looked like. You don't want to get lost in there, you never get out. And then here's a good shot on the interior, kind of on making a point about passive solar. This big window heats my house for over 2 months by now. So one big window heating the house in the really cold temperatures. I mean, beginning of mid-February, we still had 28 below. And at night, I have an R40 shutter which closes this big window up, but during the day, it allows a lot of daylight and a lot of sun to come into this building and heat it up. And it does not overheat because we have additional mass built into it where it can be stored. So now, after all the boring part, people want to always see, how many solar collectors do I have to put up to heat my house. I think I have answered incredible amounts of phone calls since my house was in the paper. People calling me up, hey, how many solar collectors will I need to heat my house? Unfortunately, that's not the answer. We need to build efficient buildings first. We need to retrofit old buildings and then look at renewable energy systems. But this is the fun part. This is probably why a lot of people are here, because they want to know, how in the world did you do this? And why is it so important? You know, it's kind of pathetic if you really think about it. We can look at solar manuals from the 1900s, and we had all the answers. I mean, Rich already showed a couple of these slides. I mean, what are we thinking? You know, it's like we're drilling for a hole in the ground. We're spending millions and millions of dollars to extract oil, and it's right in our face every day. So, welcome to the second solar age. I totally believe that within, you know, the next 50 years, we will completely transition into a solar community. And why is it the second solar age, not the first? Well, because this is where the first one we've been through. We had 100 years of a break where we burned fossil fuels, and now we're back to reality. We're starting to run out. But we have a tremendous amount of energy we can get out of solar. Richard already talked about this. We have more solar available every day than we can ever use. And that's not unobtainable technology we have to develop. It's something we already know for 100 years. So, okay, people are like, this sounds great in the Bahamas, but what about Fairbanks? So this is probably a very good picture on making the point why solar does not make any sense in Fairbanks. Trying to put up solar collectors in the snowstorm. It's a problem. What are we doing in the wintertime when the sun doesn't shine? So basically, there's been a lot of solutions which have been put into place on a bigger scale. This is a project from '96, so this is a long time ago. There's currently over 100 projects worldwide for annual seasonal heat storage systems, basically on a community scale. This heats 570 homes since '96 off solar. If we're looking at solar, we're looking at two completely different technologies. One is basically creating thermal energy with hot water. The other one is creating basically electricity. What's the big difference really? The big difference is fairly simple: efficiency. We have not figured out a really efficient way to produce solar electricity yet. Panels, basically, if you look at efficiency, solar thermal is about factor 4 versus PV, which for us really is something interesting to look at. What is our main what is our main demand? It's not really electricity, it is heating. Out of the whole 100%, we have heating, domestic hot water, and then we have electricity. So if we get rid of heating and domestic hot water, we're doing a lot better. And there's different technologies. My experience is evacuator tube in Fairbanks does not quite work well because of the really cold temperatures. They ice up and they don't have enough residual heat, and they just stop functioning. Versus the flat plate collector, which is more inefficient, has enough off heat to get rid of the ice. Typical installation is a solar hot water heater, 2 panels. You know, in the summertime we can produce some hot water. That doesn't give us any heating, that's for sure. So if we are going to heat houses at the same time, we need something different. And I call this like a microhybrid energy system. We need to collect more than just one energy. We need to collect multiples and store them and have the ability to bridge time, which we do with seasonal storage. So on my house we have 480 square feet of thermal collectors. They're 4 by 10. It burns very hot, and we can capture all the energy. We've by now designed a system around it which basically makes domestic hot water at the same time. I can produce enough hot water for my family of 4 in this house, and heating with 1 fire in the morning and 7 watts of energy of running a pump. That's not too bad. Big part of it is this energy system, which is based around a 5,000 gallon storage tank. On the first project, we buried the tank outside. We learned that that might not be the best idea. I put it now within the building. It stands upright so that it can stratify. We need high temperatures, low temperatures, and we're producing basically domestic hot water with a tank and a tank design at the same time. This tank sits at 160 degrees completely, bottom to top, 5,000 gallons, since mid-February in my house. So I have about 2.5 months of hot water and I have no heating demand. So I really screwed up. It works too good. I can run hot water on 2 tubs wide open for over an hour before I drop below 120. It's incredible. So yeah, solar doesn't work. This is basically the guts of the building. That's the inside of the tank. It's a stainless steel tank, 40 gallons, which is bolted in the top to convection that is heated from the thermal mass of the big tank. This here is a custom-built solar stratifier. That's basically nothing else other than 8 inches of CPVC, which I bought for a few $100s. All of this stuff is off the shelf. The tank is a salvaged old fuel tank I cleaned up for, I bought it for $1,000. It's not a stainless steel tank, it's an old fuel tank. I cleaned it up and I purchased, as you can see here, a liner basically. There's a company in California which makes liners specifically made for heat applications. Lifespan 15 to 20 years. So it lives in the middle of the building. We never want to take this tank out. We never want to have a leak, so we put a liner into it. We have a manhole on the top. In 15 years, we're going to drop this liner out, put a new one and start all over. It's not really too difficult. The parts in this it's really cheap. There's a couple of $100s in the piping. It's very low key. There's no moving parts. It all works by physics. And this is all the engineers in the room can laugh now. This is my art drawing on it. I don't really want to go too much into it because this is the 2nd generation, and by now I'm at 4th generation. We're improving this day by day, and I learn every day on it. But I see a lot of potential. But in a nutshell, how does this work? We have heat from the collectors, hopefully. The collectors and the house side is all based on glycol, and we can heat the house directly from the collectors. The slabs basically can gain directly heat out of the collectors, or if we have, like right now, no heating demand, we store it in this tank, and basically it just drops in. Depending on its weight, its density, it finds its own weight density within the tank, and I can start my collectors in the morning at 10 o'clock when we have maybe 65 degrees and heat up the bottom, which is maybe at 40 degrees. And then during the day it will come up. So we don't have this problem of a domestic hot water system. 120 degrees is our target. A BTU is a BTU, so we want to collect as much as we can. And this works really well because it can collect all of these different temperatures. We can heat a house with 70 degrees, and we don't need these high temperatures, which we don't have available when we really need it. But just as an example, February 1st, I pulled 180 degrees of hot water already off my roof. So it works really well. I had 38 below at the collectors at 8:30 in the morning. By 11 o'clock, I pulled 134 degrees at 24 below outside temperatures, and by high solar noon, I pulled 180 degrees. So it's not that this can't work. We just have to design it right. And for us, the solution really is in a community-based solution, in my opinion at least. This is an example out of Canada. This is the only one we have in North America. There's nothing in the United States, and hopefully we will see one in Fairbanks. It's at least my goal. It's basically, we take this concept to a bigger scale, which makes it more affordable, makes it more realistic, and we take it makes sense anywhere between 30 and 60 homes. And we do a community-based heating storage system. We basically, Drake's Landing has about 800 collectors, which dump into this heat store, which is fairly easy to build. And it makes a big battery out of the ground. It's heated up all summer long, and then in the wintertime, it's drawing the heat back out. It takes about 2 to 3 years to get this thing up to charge, but it works. I mean, there's over 100 of them worldwide. Germany's by far the leader on them. They have many, and a lot of them in production. And it will work here just as fine. It will even work better because we have so much sun in the summer. Some interesting numbers. I always kind of like to throw this up because we always think, we're so ahead of the curve. let's look here. This is us. Currently, right now, South Korea has more solar installation per capita than United States of America, and they have a solar community heat storage already built. We're really not ahead of the curve as far as solar goes. Energy consumption worldwide, primary energy supply, we're at 0.7 for renewable energies right now. If we ever want to get to 100%, we better hurry up. So key lessons, what's really important to make this all come together? We need good teams. We all need to work together. We need to get off our egos of thinking, oh, we have all the answers. We don't. We need to work together. We need to find answers together. And we need to work together because we have a common problem we need to fight. And we need to re-look at, what is a building? And technology is really there. We have a lot of good tools. We can figure out where's the best solar radiation. We can figure out air tightness, fairly simple. And we need to build efficient buildings. Any building we built, I would say 95% of all the buildings in this town built today are crappy buildings. That's the short of it. And that is very sad. It could be an opportunity, but it is a liability. We will remodel all of these buildings in the next 10 years because nobody's going to be able to afford these houses. I mean, $5 of heating fuel, who's going to be able to afford it? Nobody. Key things to remember: insulation, insulation, insulation. Something not everybody's familiar with is thermal bridging. It's basically take a piece of metal and heat it up on one end and hold the other end. What happens? You're at one point going to get very hot. And that's the same thing on buildings. We cannot afford cold to travel into buildings, so we need to design accordingly. We need to build airtight. It's not difficult. It's just a matter of design and practice. And the biggest part for me really is none of this would work if the building wouldn't function as a system. It's all about making everything work together. And I said it before, and I say it over and over and over, air tightness is really the only cheap methods we have. If you're trying to figure out right now, how can I save more fuel, you got to figure out your air tightness. And right at the same token, you need to figure out how you're going to get fresh air into your building, because otherwise you're going to have another problem, which a lot of problems, we're having in our buildings anyways, but we have to breathe. For reaching real good air tightness, we basically need to just design continuous air layers. That's all stuff we have. You go on Cold Climate's page, you can download a manual. We've written about a lot of these things. Minimize penetrations. And then one argument I'm trying to make with Alaska Housing for many years is we need to pre-test our homes. Before we start doing energy audits right now on any new construction is done at the end of the project. When it's too late, we can't fix it. We need to do another test after all the rough ends are done, before the walls are closed up, so we can find leaks and fix them. It's so simple, it's so basic, it makes so much sense. I don't know why we're not doing it. Then in our climate especially, windows really is the key. Windows and doors are the weakest link. It doesn't make any sense for us to put windows in the north. They're a loss, there is no input. Oftentimes it's difficult to do, but we should at least minimize it. We can overcome the R value, which is not there in windows, with thermal shutters, but we cannot afford not to have sunlight being able to put its energy into the building, which is called solar heat gain coefficient. And if you look at most of the windows on shelf sold in Fairbanks, they are not looking at that at all. People don't know what this number means, but that is so important. It's not about the R value, it's about how much energy can be captured. And in my opinion, in the south-facing building sites, it needs to be at least 60%. A lot of the bigger brands in town sold are at about 12%. So next time you go window shopping, make sure you look at that. And there's only one free energy you're ever going to find in a building or in general. That's passive solar. No maintenance, no nothing to it. Will never break down, never change a pump. It always works and it's free. Windows is what we need. Better windows is what we really, really need. We have good windows. We have two good window companies in town which can make insulated fiberglass windows. It's not just about the window, it's also how is it installed, and that is very, very important. We need to install these windows halfway within the wall, and we need to over-insulate the frames. That's basically shown here. That keeps the edge warm, which is the spot where we have the biggest heat loss. And Passiv House has done a big study on this. I've learned this the very hard way over the years, and it's very interesting. It's about 20 to 22% efficiency increase with the same window, same material, just change of installation. Now, this is the weakest point of our installation in general, and we're gaining for free more or less 20%. That's huge. Put a thermal shutter on it, and then we're basically where we need to be. And then it's cold, and in the wintertime you have 40 below air, and a heat recovery ventilator to bring fresh air into the building can only do so much. So I'm a firm believer we need to start pre-warming that air, and that's fairly simple to do actually with a small geothermal loop. 400 feet of pipe is all it takes. Doesn't take much electricity to run. And I can run my HRV at 40 below with a 3-degree temperature differential between supply and return. Doesn't mean much for the average person, but anybody who understands the physics of that, that is incredible. Basically means, I pull in 40 below air and I only lose effectively 3 degrees. So I dump out 70 degrees air and I'm still at 67 degrees. It's a big, big, big advantage in our climate. And then I really believe we need to start looking at the basics. Where is efficiency in design? We need to not think about how do we heat this place. We need to think about how do we keep the heat, understand heat loss, make it work for us and not against us. Size matters. We need to build smaller. There's plenty of 10,000 square foot houses we built last year in this town. I don't think that's so advisable anymore. Keep it simple. I showed very complicated stuff here about my solar thermal system, but in reality it's really simple. There's nothing to it. There's 4 pumps and there is less plumbing. There's about a third plumbing than there is on a boiler. Figuring it out and making it all happen was the hard part. It's not complicated. True costs of super insulation. Now that is of course the big crux, and I'm fighting this all the time. I have lots of people coming in and they're like, I want this efficient house but I can't afford it. What am I going to do? And I don't have a good answer for this. That is a problem with our financial situation we're all stuck with. The truth of it is we need to look at not just the costs to build anymore, operating costs and lifespan, especially operating costs. On a commercial building, that's 84%. On a residence, that's still way up there. What does it mean, really? The money is not in the building. It's in running the building. And right now, all the cost analysis we do is on the costs of the building. And energy costs, unfortunately, as we experience every day, are a moving target. And God knows where are they going. Hopefully I'm wrong and they're going to come back down, but I have my doubts. And if we look at the global, not just at what's happening in the United States, but if you're looking at a global scale, what we're seeing right now we have never seen in history. And there is no real value anymore, anywhere. Everybody's borrowing money from anybody. Our deficit is so high it cannot sustain itself. A daily basis of $10 billion. It's just unheard of. There is no answer to it. Right now we are in free fall. And it's just a matter of time when we're hitting the ground. And being somewhat prepared will help, but we're already late. If we're looking at the 2 costs, the bottom line you see basically is your average house, and then going up. Passiv House isn't even on this study, but passive house would be up here. You know, it pays back from day one if you look at true cost of ownership. And that is really the only thing we need to make bankers, appraisers, and our government realize there is money to be made with this. If we are super insulate our buildings, we all ahead of us. And it makes, not just for us as comfort, but also for our economy, it makes sense from day one. That is my strong belief, and that is something we all need to work on. And this is the big thing, one of the key messages I want to really give everybody home here. Think about this, you know, any new building we built today can either be an opportunity, or as 95% of all the buildings we built today are a liability, which we will go back within 10 years and fix. Any building, you know, if you're trying to build a house here anytime soon, think about this. Do you want to go back in 5 years, in 10 years, and completely redo this house because you cannot afford living in it? Does this make any sense? It does not. So think about it clearly and keep your eyes wide open. But the opportunity is what we're really needing to look at. And then there's a lot more in buildings than efficiency. I'm going to just go through this real quick. We shall not forget where we are coming from, and that is something, you know, another complete different problem than efficiency, you know, as far as energy consumption goes. But we need to look back at, you know, where are we coming from and what makes us humans, and what is actually a building to us. Is it just a shelter, or should it be an extension of ourselves, some place where we can feel comfortable, not just thermally, just also as humans? A place, this is a shot of Caucasus House on the inside, which to me captures this feeling really well of we're bringing the inside back to the outside. We're feeling at home and we're feeling comfortable. We're creating an environment where air can move, where we have fresh air, where our children can grow up and feel that connection to the outside, which a lot of us are really missing. And that is an even bigger problem in our modern buildings, in my opinion, than energy efficiency. We completely disconnected with what makes us human within buildings. And in the future, I strongly believe we will not just look at high energy efficient buildings, but we will build living buildings. And there's no way around this. This is the only sustainable way we're going to be able to live and build in the future. This is not going to be tomorrow, but this will be sooner than we might expect. Buildings will create basically their own heat. They will create their own water, rain collection, grey water recycling, and they will keep everything on site. And that is something we can do already today. Technology is there, knowledge is there. It's nothing we have to invent. This is nothing unobtainable. This is today's technology. We're just not putting it into place. Because we're saying it doesn't make sense economically wise, but it actually does if you're looking at it properly. And the first thing I really wish Fairbanks would get would be a passive house school. If we need anything, we need better education for our kids, so that they're growing up a little smarter than us. People often ask me, why are the Europeans so far ahead of us? Oh, it's energy costs, but it's not just that, it's education. The kids are growing up in a different environment. They learn a little bit different about what's important, what's not, and that I think is the big difference I see. Any building conference I go to in Europe, there is no haggling about climate change, about this, about that, energy costs, will they go up or down? Nobody argues about it. They're more focused on, hey, what do we need to do to cope with these challenges ahead of us? Versus here, we're just around the table arguing. And anything we do in buildings, we should always remember that our health is priceless. We are building buildings which are very, very bad as far as health is concerned. We are not taking proper precautions on what makes homes actually livable. And before we look into energy efficiency, we need to look at health. Health is always what needs to govern everything else, in my opinion. And not least, let's not forget we only have one of these plants around for right now, unobtainable again. We should really take care of it before it takes care of us, and that's what will happen sooner or later. I always say please build responsible, and if there's any questions, I'm 3 minutes late, but we might have a few minutes left. Thank you.
So Rick, why don't you come up and then we can have just a few questions. I know we're going to need to get out of here fairly quickly to get ready to move each, but there's a lot of you here and we've got some questions. Yeah, in the back.
So you mentioned two companies locally that build really good windows. Can you say what they are?
We have,
Thorpe, and
yeah.
you guys could repeat the question. That'd be
Yeah,
great.
well, the question basically is two local window companies, whom to choose, or who is that? There is Pioneer Windows, basically, which makes insulated fiberglass windows. I think actually there's three by now. Let me back this up. Haus-The, I think, makes fiberglass windows now too. In our cold climate, vinyl windows do not work. You cannot make vinyl windows work in a super insulated house. The material flexes too much. There's too much give in the wintertime. One winter and the best insulation is shot. Fiberglass is really the only material I found which works. So there's Haus-The, there is Pioneer Windows, and then there is Greatland Windows. Greatland Windows is currently the only company which makes tilt and turn windows with a much better locking mechanism, German hardware, sorry. That's what we use, because it really allows that over insulation and the better window installation a lot easier than the typical North American windows.
Thorsten?
Yeah.
Your standard, you went to Passiv House standard, is that what you did for your air exchanges?
Yep.
Okay.
Well, no, let's back this up. I can't, of course, it's, we're governed with air exchange with ASHRAE, with what our building code mandates. But what the homeowner actually does is a different story. No other questions?
What is the liner of your water tank made out of?
It's a 60 mil, it's HT something. It's specifically made for industrial applications. It's made for it's rated for continuous heat at 200 degrees. Design temperature on my big tank is 180 degrees basically, which is about equivalent of 5 million BTUs.
And what kind of,
Did you say no vapor barrier or no 6 mil poly vapor barrier?
Question was there no vapor barrier, which is a good question. The building doesn't have a classical vapor barrier. There is no plastic within the wall. What I basically use as a vapor barrier or an air tightness layer is CDX plywood. It's basically the qualities of wood. It allows diffusion, but it's airtight. Best example for me is, let's assume we go for a 10K run, and one of us is in rain clothes, rain pants, rain jacket, and the other person is in a Vortex suit. Who will be more comfortable?
how much the passive solar technology and air exchange stuff is usable in the lowlands of Fairbanks?
That's question basically is how much is available in the lower ends of Fairbanks. Rich, you want to answer that?
What do you mean lower ends? Well, anything, if you're in a spruce bog, how much does passive solar works? How much of the buried,
I mean, the short of it is you have to have sun to capture it. If you don't have sunlight available to you, then you're kind of screwed.
Why cellulose instead of blown-in fiberglass?
I'm pro cellulose too. I did this on my retrofit. My personal reasons are it's a whole lot less hassle to blow. It's cheap. It's not scratchy. It doesn't have all the problems of fiberglass. There's nothing wrong with fiberglass, but cellulose is inherently, it's also a local product. You can get it all in state from, it's a recyclable natural material. Everything about it, embodied energy is low. I just love cellulose. The only thing wrong with it is don't ever let it get wet.
Heat storage capacity of cellulose is much better than fiberglass. Fiberglass is, in my opinion, a very poor product, and we're 74% of the market share is basically held by fiberglass companies. That's why everybody's using it. But why that is beyond me.
What kind of house wrap did you use? I thought it was Tyvek. Did you
Yeah, it's just regular Tyvek.
use regular Tyvek?
Yeah,
It's not drain wrap?
no. No, and we used basically over the plywood Tyvek, which I would not do anymore, which was kind of a conservative approach because a lot of very important people were nagging on my ear that this never will work. And I caved in, and now actually it works really well, and I will never go back to the Tyvek because I think it actually would be more of a problem than not.
This HRV preheat strategy, the 400 feet, was that some kind of a fluid circulated, or you ran 400 feet?
Yeah, no, it's basically, it's a closed loop system. It's 3/4 inch PEX with a glycol-based fluid, which is
Is that a
pumped.
second kind of a heat exchanger?
It goes through a plate exchanger basically, which the incoming air goes through. Again, it's German technology, I'm sorry. It's a German HRV with basically everything is a plug and play. They have it all built in.
What's the company?
Zender.
How do you support all that cellulose in the attic? Were you plywooding the ceiling?
Yeah, of course, you cannot just put sheetrock up, and you shouldn't anyways. Again, we need to look at vapor diffusion and how do we seal this attic space. The only way I found that to work actually in reality is by building a failed ceiling. We do that with 2x4s. We built a 2x4 failed ceiling. We sheet the top with 1/2 inch CDX and then air seal that and then roll the trusses right on top of that. And then the failed ceiling is basically attached to the trusses with longer screws to make it structural sound. But that basically allows you to have all your electrical lighting, everything has a utility chase. And again, we have no penetrations in the lid, and we have the extra strength we need for that weight of the cellulose. I mean, there's a lot of weight. Cellulose is heavy, 12 tons, that's a lot of weight.
So unfortunately, we're only gonna be able to take one more question, but I'm sure these guys will stay after.
Yeah, I stick around. If anybody's more interested, find me, we chat.
Remind everybody you'll be in Esther tomorrow.
Oh yeah, I forgot, of course. I was supposed to mention this. I'm gonna give another spiel tomorrow in Esther at the library at 7. 7?
The hall, Parkland Hall, 7, yes.
Harthen Hall, Esther Library at 7 tomorrow. So if you didn't have enough, bring the tomatoes tomorrow.
Any plans in the work for the Passiv House community or ideas for location?
Yeah, I'm trying very hard to get a Passive House class up here. And I'm also working with Passive House Institute to lower the number we need to achieve to certify buildings appropriate for our climate, because the only way you can do this right now is basically with thermal shutters, and they're expensive.